this relationship, and then, you know, we are in a ring, so we can wrap around, but I don't have a ready example.
I mean, outside of a case where like n is equal to 2 and then is equal to 3, it seems like that is an unlikely scenario.
So, okay, so what is the problem? You think that the stabilization protocol isn't necessary?
No, I was wondering like why we were getting into this configuration where you.
Oh, so like it's fine if the answer is you can't ever get into the configuration.
Yeah.
But I think we should be wary of that kind of thing because as I'm going to talk about at the very end of class, there are a great many configurations that the Chord authors said the system can't get into. In fact, which they proved it can't get into. But they were mistaken, it could get into them. So we should ask ourselves, we should say, are there pathological scenarios, whether or not we think they're likely to happen in practice, and what would stabilization do in that case? But you're right, maybe that would just never happen. Okay, stabilization. Fault tolerance. So we did replication. I think we're done. I think we're good. Any questions about Chord and how it maintains a ring before we start getting into the when it doesn't maintain a ring?
How does it interact, the stabilization and joining nodes interact with the failover thing? Like, because you're looking at some of these predecessor and your successor at the same time to figure out if they're still there.
Yeah, I mean, to be fair, I think like one of the things that's swept under the carpet a little bit is that in a regime in which nodes are frequently joining, some of the benefit that we get from consistent hashing is squandered by lots of data movement that happens among adjacent things, possibly even in a thrashing way, due to stabilization. Right? When I do stabilization and I disabuse myself, there's somebody who belongs between us, data needs to get moved around every time that happens. Right? So there is this question about like how often, from an engineering point of view, at what rate of churn does the fact that you're doing consistent hashing not help anymore? Because you're doing all this movement in really small regions anyway. And the fact that you've like localized your movement to small regions doesn't help if you're literally moving all of the data in a hot potato fashion in all of the regions. Does that make sense? I think that's a legitimate systems engineering concern that it would be tempting to ask in simulation. You're like, at what rate of churn on my x-axis do I stop seeing the benefit of consistent hashing? Because I'm actually bottlenecking on this other thrashing issue. It's unrelated to global movement of data that you can see in hashing. It's really interesting. Yeah, so I would be interested. I would read that simulation study. So I guess the first thing I should say is, so yeah, Chord was published in SOSP, which is the most prestigious systems conference, 2005, and it won Best Paper. And it was like one of the first systems papers to come with a whole bunch of like rigorous proofs about its correctness. There's all this text in the paper. It's like, to the best of our knowledge, this is the first peer-to-peer system that has come with correctness proofs. And they have this huge list of proofs. Things along the lines of, due to stabilization, if a particular key is ever reachable by a particular node, it always will be in the future, despite concurrent joins and leaves. That's a nice problem. Like if I can reach, in some sense it's like it's read your rights. If I can reach a node, no matter what, things are coming and going, and tornadoes are hitting data centers, and routes are flapping, and I can always get to that. I think that's amazing. And the other really important one is the so-called the one ring property, right? Which is like based on the protocol that we just described, stabilization, join, if somehow it was ever the case that we ended up with two rings, now how could that happen? Well, you could have a bunch of nodes join and leave in just the wrong way, maybe, I don't know. If this were true, no amount of stabilization will ever, like the twain shall never meet. And we'll never be able to do, we'll never be able to look up something here and be able to address it over here. So this is pathological. If the ring was ever broken, it cannot be reforged, So arguably the most important invariant in the paper, and it's proven in the paper. It's like proof. You can't read it, your eyes glaze over. But the thing about proofs written by human beings is that they were written by human beings. And so it's very often the case that I read a proof and I'm like, you had me at the intuition. Because if you want to believe something. Yeah. So I don't know, I just, maybe the takeaway from this is just don't ever believe a proof written by a human ever again. So there's a researcher named Pamela Zabe at AT&T Research. And she used a lightweight modeling tool called Alloy. Really cool, developed by Daniel Jackson and his group at MIT. And in Alloy, which is sort of like a logic language for modeling systems, she modeled Chord. She didn't implement the whole thing in C++ like Stoica and his people did. She just modeled the fundamental APIs, fundamental protocol algorithms. And she proved via counterexample that many of these properties, including the one-ring property, didn't actually exist. So that is to say, she demonstrated what we call in this class an anomaly, an execution with a relatively small number of nodes and a relatively small number of operations where at the end of that execution there were two rings. Right? So she proved by example in a finite execution that the one-ring property didn't hold. Right? It's super cool. So let me see. And what's really surprising about it is that the example is just dead simple. Okay, let me see if I can do it. So it goes like this. Let's imagine that there was Alice and Bob. And Alice was Bob's successor, and Bob was Alice's successor. Now remember, as I told you before, in order to maintain fault tolerance, we always also maintain a successor of my successor pointer, right? Which at least in this trivial example would look something like this. In fact, I'll draw that as a dotted line. Alice is the successor of Alice's successor, and Bob is the successor of Bob's successor. Everybody with me? This is a ring. This is fine, right? We can route on this. Suddenly, Derek and Eleanor appear and join the ring. And they belong in these places in the ring. So Derek has somehow routed his way to Alice. We've repaired pointers. He's routed his way to B. We've repaired pointers. And the protocol specifically says first, atomically, Alice is going to update her pointer to E, with E updating its pointer to B. Similarly here, B updates its pointer to D, and D's pointer remains there at A. Step 2 is to repair the successor of the successor pointers. And so what we would want is, after this operation completed, and we had our basic ring, and we thought, everything's okay, now we can route, good. Now we can say, oh, actually, the successor of Alice is now Bob, and so on. Unfortunately, at this critical moment, these two relative newcomers also immediately crash. Totally can happen. Route. Two rings. And now people can come along. Now this was in the imagine like in the first minutes of the universe, somebody really fucked up. And then everybody starts coming, and now we end up with this giant ring up here with people who joined Alice and this giant ring, but they'll never talk to each other. Right? So, not one ring. And the takeaway is just, it's easy to prove things that we are already convinced of, and it's easy to believe that a proof goes through if we believe the intuition. We really need the help of computers to understand what's true. Okay. Questions? Isn't that cool? What's so cool about this is it's a really small example. And in fact, Alloy would have blown up if it was any bigger. See, Alloy doesn't do so good with big models, right? This is really frustrating for me because in my lab we build bug finders for distributed systems. And we try to find bugs by analyzing the systems and injecting faults and trying to drive them into bad places. But my system couldn't have found this bug. And the reason is because this bug didn't just involve faults. It didn't just involve Denise and Eleanor crashing at just the wrong moment. It also involved them coming around at just the wrong moment. So it involves a very precise interleaving of input events and failure events. And I happen to have written this solver that all it does is failure events, and so it would never find even this trivial thing. But I don't feel that bad about it, because Jan Stoica, the guy who won that paper, didn't figure that out. Okay. Cool. So I wish I hadn't gone on for so long. Data parallel stuff. So let's imagine, I want to do an exercise. Something completely different. Let's imagine that, I don't know, I had this giant fleet of computers. And I thought, well, I have so many computers, there's got to be ways to do stuff fast, right? All these computers. And, I don't know, let's just say that all these computers, randomly distributed, they've just been placed there by some random process, are documents. Word documents or web pages, or I don't care. But the point is they're randomly placed. They aren't partitioned in any particularly cunning way. I don't know where anything is. Okay? And what I want to do is, I want to do sophisticated things in this. This is kind of the workhorse example, right? What I want to do is, these documents have words in them, right? A document is arguably, reductively, a list of sentences, and a sentence is a list of words. So a document is a list of words, right? But I don't want the documents. What I want is the words and the number of occurrences across all the documents, with the expectation that a great many words are going to be in all of the documents, because words have a Zipfian distribution, right? So I would expect that at the end of the day, the word "the" occurs in nearly all of the documents, you know. But the word "lazy" occurs in some, and the word "anti-disestablishmentarianism" occurs in just a couple of them. And plus, there's all those misspellings of words that are all going to occur exactly once, right? Unique misspellings of words that only happen once, right? Zip distribution. So I want to compute this, and this is my input. And I have lots of parallel resources. And just to make the problem not trivialized, let's imagine that even this list, which is obviously much smaller than the complete set of documents because of the compression we get here, is still too big to fit on any one computer. So at the end of the day, the answer to this distributed computation is going to have to be distributed in the same way that the input was, but maybe not on as many computers necessarily. But it has to be on some computers because it's too big to fit in memory. Okay? Computers can fail. So let's imagine that each document is stored on at least 2 of these machines, or else the loss of the machine will mean the loss of documents. I would like you to take 10 minutes and break into groups as we have in the past. And at a high level, not writing an algorithm, but at a high level, describe, so you're all distributed systems programmers right now, you know how to make computers work together, synchronized, blah, blah, blah. How would you make this, now remember, there's always the straw man, but if I didn't have the constraint about memory, the straw man is send all this stuff to one machine, and then parse the documents, and create a hash, and do what you do. Okay? We can't send them all to one machine, because it's too big. We also wouldn't want to do that, because we would squander all these parallel resources. Right? We want to maximize the work that gets done on all the machines. But take 10 minutes. Tell me what you think we would do.
Client wants to know how many lazies there are. It would go to the corresponding computer, which would have that subset of the whole document.
Yeah, that sounds about right. That sounds about right. I mean, I guess there's a couple little things, which is like, how do I avoid processing this document twice, since there's 2 of them? Or do I just double the work? Because then that means that's gonna half our throughput right there. So that's one issue, something to think about, but that's cool. And then what about fault tolerance? So what if we got almost to the end of the computation and then a machine crashed? Will we have to start over?
Well, it's distributed computation.
Uh-huh.
So you have the results on other machines that do crash.
Not necessarily. I would have to take special care to make sure that the results are as redundantly stored as the input was. Right? Yeah.
For the first problem, whichever machine or machines will be the ones containing the shard or shard data. The sending machines with the documents can also send the hash of the document in some way, either the name of it or the entire contents. And since there's multiple, for every document there's like a word count, and since if there's a duplicate hash, then just don't add that to existing lists.
Well, I mean, I kind of lost you in the beginning because it sounded like you were saying that you have to send all the documents across the network, which surely can't be.
Well, no, it's the hash of the document where the word count is, and the word count for
Right, but then that means that the computers that are storing, like imagine this computer that was storing this slice of the word count and whose memory was just sort of big enough to store this slice of word count that was hashed out, also needs to store all of the document IDs that contributed to it. That seems like too much, right? Because in some sense, like literally all of the documents contributed to the count of the word the. Right? So that's a lot of metadata to store. So that might not work. So I guess like at a high level, yeah, so this works, I think, but stuff that hasn't been dealt with that you would need to code around is how do you tolerate failure? How do you recover from failures in particular? How do you like schedule this computation? How do you tell things to start going? How do you use a scheduler maybe to make sure you only do a piece of work once rather than twice? But I think at a very high level that works. And thank you. You can sit down. Thanks. That works. So what was the technique? The technique was massively parallel processing, pushing the compute down to where the data is. So do work as much as you can without moving any data around. And then when you've reduced the data as much as you can, share it around. Unfortunately, it turns out, of course, that when we do this, what does the communication pattern look like? Let's line up my machines like this. These are all of my machines, and here they are again. When I hash the data, and I had to draw arrows of data movement, what do those arrows look like? So it's going all, who said that? They're just going all over the place, right? So it looks like this, right? It's like, well, okay, I have those, and you have those, and you know, so this is called a shuffle. Right? In some sense, there's no avoiding this, right? Because the data was partitioned according to the documents that contained it, and now we want the answer to be partitioned according to the words that are in it. They're two different partitionings. Luckily, this is a lot less data than the original data set. We've reduced the size of the data massively by doing this local computation, in particular because we've forgotten about the documents. Okay? So this is just, I mean, we're out of time. This is just to say, if you did this yourself, you could do it because you're smart programmers. But what the Google engineers would say is, most of what you just did is like a reusable recipe for parallel computation that can be used to solve lots of parallel computations that we do at Google. Right? The only thing that was specific to the word count problem was the fact that in this first phase, we counted words. That was a few lines of Java. And in this last phase, we like summed up the numbers associated with each word. Right? So the idea that Google had with MapReduce was, we should provide for users, because so many large-scale computations look like this, we should provide to users a framework into which they can plug in the sort of task-specific logic, and we can have an infrastructure that takes care of replicating the data, partitioning the data, making it fast, recovering from the loss of nodes, blah, 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 blah. So in the next lecture, we'll get into all the details of what the MapReduce system looks like. But real quick, what's a framework?
It's like 19 JavaScript groups. Somebody say something.
I have a definition of framework that I like. I'm just curious what you all think. What's the difference between a library and a framework? Yeah.
I guess you could say like a library is something you use, but a framework is something you follow.
Oh, interesting. I was going to say, library is something you use in Russia, and a framework is something that uses you.
Yeah.
So, imagine this. I've written some code. Now, do this, then do that. Lather, rinse, repeat. I own the code. I own the control flow. But there's some code that I don't want to write, man, because like, I don't want to compute a checksum. So there's code in the library, and what I do is I call out to the library, call the function returns, I own the control flow. I know when I block until it comes back. So the library provides functionality so that me, the god, can not have to do everything over and over again. And then typically a framework looks totally different, right? A framework looks like, remember, the left is me, and this is them. You know, whatever support is provided by the system. In a framework, they own the control flow. There's this program that's going to do X, Y, and Z. But the thing is, there's some holes in the program. But it's unspecified what it's supposed to do. It's supposed to do some setup, run the code in the hole, do some cleanup, run the code in the hole, do some final cleanup, and that. And the user is supposed to supply code that goes in the holes. So these are sometimes called hooks. And so a framework might provide you with hooks. You provide some pieces of code, and the framework orchestrates your code at the right time. So MapReduce is a framework in the sense that it's doing scheduling, it's doing fault tolerance, replication, blah, blah, blah. Every now and then it's like, oh shit, I have to count some words. Word count, yeah. Oh shit, I have to sum up some things, or sum. Right? And Google's observation is, this doesn't change. This is what changes. So you tell programmers, you come up with a real simple language that can describe two phases of computation, a massively parallel phase that works on the raw data, and a combined phase that mushes data together. So this would say count words, and this would say sum them up. If you can get your users to use this programming model, where they just say these two things to do, you can do them smart, fast, fault tolerant, etc. So in the next lesson, we'll look at what these things might look like. So what are the, I don't have time for that.
1 minute.
1 minute? What else besides word count fits into this framework? Well, a really common thing in web search engines is document indexing, right? Where what you might want is a list not of the words and how many times they occur, but a list of the words and the documents that they occur in, right? Because if I had a term vectors like this, and I wanted to look up the lazy in Google, Google could just look up the term vector for the and the term vector for lazy and take their intersection, and those are the documents that have both those words. That's like what web search used to look like 15 years ago. Or maybe I want to do distributed grep. I want you to print out all the documents that have the string Peter in them. Well, that's really easy, because I just write a map, I write this function that says, if you see the string Peter, print it, or something like that. And so I go through this whole laundry list of these things that you always want to do at large scale. And they all kind of like have this common part that's like hard and distributed systemsy, and there's a way to fix it. And this unique part that's just programming on a single computer kind of stuff. Okay, I will send out the map newspaper for you to read tonight. Thanks everybody.